Okay, so before we start, is there any questions? So, did we decide the final exam date? No. Not yet, right? Okay, so first day of June. And so the exam period will start on 15th until 21st, right? From Thursday to Wednesday. So we have two possibilities of 15th and 20th, right? So Thursday and next week's Tuesday. So yeah, let's do a poll. The earlier one, 15th, earlier one. Okay, later one. Okay, then probably we'll have an exam on 20th. Yeah, but I'll do this poll quickly. I mean again, if we have more students later today. Okay. Okay, so we will finish. Yeah, we will finish eigen decomposition today, and then move on to chapter 7. Yeah, which is actually really exciting to me because it's my first time to go beyond this eigenvector and eigen decomposition. Okay, so let's finish up first this eigen decomposition. Okay, so yeah, we basically discuss this eigen decomposition corresponding to the first line, and then the diagonalization of the corresponding to the second line. Yeah, so both of which are the same with each other. Yeah, essentially the same. And as I mentioned, we are changing the matrix A into some diagonal matrix D by multiplying some matrix P on the right and its inverse on the left, right? And then what kind of matrix of P will it be? So what matrix will P be? Okay, so that A becomes diagonal matrix D, and then what will be our resulting matrix D? Okay, so that was the main issue in this eigen decomposition. And it turns out that the matrix P such that the matrix A becomes diagonal matrix. It is contained. Yeah, it is actually a set of eigenvectors, right? And the diagonal matrix D is a set of whose diagonal entries are your eigenvectors, right? So that was our main key part in this key part in terms of the relations between eigen decomposition and eigenvalue and vectors that we learned. And yeah, this kind of transformation can be changed into this form, right? The second one, AP equals PD. And then we kind of proved from this part and this part, from these parts, we were able to understand why the matrix P should have the columns as eigenvectors, and this D part, why it should be our eigen values, right? And yeah, actually this kind of manipulation of, yeah, starting from these separate eigenvector value relationships, right? We initially had a 3 different eigenvector value pair with its own eigenvalues and eigenvectors, right? And here the key part was we can integrate them really nicely into one single form, like this, and then this. And so we can combine all these 3 equations into one single equation of AP equals PD, right? That's how we can arrive at this AP equals PD. And here, okay, so here let me ask a question. So in this case, your matrix A is 3 by 3 because your eigenvectors are 3-dimensional vectors, right? So A should be 3 by 3, okay? And what if you found only just 2 pairs of eigenvector and values, okay? Just 2 pairs of an eigenvector and value pairs. So in that case, we will have 3 by 3 matrix A. So I'm just rewriting AP equals PD. And we will have 2 eigenvectors, V1 and V2, and this will equal to V1 and V2, which are set of, whose columns are eigenvectors, and our D will be 2 by 2. Is it right? 2 by 2. So it's a 3 by 3. And what is the size of P? 3 by 2. And 3 by 2. And so AP, yeah, it is composed of 2 columns, AV1, AV2, right? So we have 2 columns as a resulting vectors or matrix. And 3 by 2 times 2 by 2 diagonal should give you 3 by 2, right? It's a 3 by 2, and it's a 3 by 2. The right hand side is also 3 by 2, and our matrix will be lambda 1, lambda 2. Okay, and in that case, the right hand side will be corresponding to lambda 1 v1, or as I mentioned last time, it can be viewed as the linear combination coefficient that linearly combines those 2 columns, right? And so the corresponding coefficient is lambda 1 and 0. And so this lambda 1 v1 and lambda 2 v2 as our resulting matrix. And this is also 3 by 2. Okay? So at this point, this equation is clearly true. It's true so far, right? But in order to change this equation as the similarity transformation, so that P and P inverse becomes diagonal matrix, will it be true? So can we change this AP equals PD into this P inverse AP equals D? So it is not possible. So it is not possible. And why is it not possible? Why is it not possible?
Are we not sure about the existence of P inverse?
Yeah, that is right. Yeah, you're right. So let's see. So here we have to guarantee that we have to require some assumption that P is invariable matrix. Okay, so that means at least, so in this case we already know P is not invariable. And why? yeah, even before talking about its invariability or whether the inverse matrix exists or not, this matrix or P part is not square matrix, right? It's not square. So we cannot even talk about its invariability or its inverse matrix, right? So we at least have a square matrix for P part, which means for 3 by 3 matrix, we need 3 columns in order to form or create. In order to create P, we need to have 3 by 3 matrix. Okay. Okay, and then yeah, we are still kind of briefly reviewing what we learned from slightly a different angle. And then what if we have, yeah, so what if we just duplicate the second column on the right of P, and then we just copy the second column into the third column just to make our matrix as a square matrix. Okay, and then now it has some possibility of having an inverse matrix of it. And then yeah, in that case, this diagonal matrix should be now what should its size be? What will be the size of the new matrix P? Sorry, the new matrix D. It's a 3 by 3, right? 3 by 3. So then what is this value? What is the last one? What is the last one? What should be the last one? What should the last one be? Okay, originally, so this guy is a V2, right? So what will be AV2 equals? Okay, so now we have another column V3 in the P part as well, and this guy should be lambda 2, right? Because we just simply duplicated or copied just the existing or previously used eigenvector into the third column, and then we can just simply bring its corresponding eigenvalues, okay, into this part, right? Okay, and now we made our matrix P as a square matrix, but is it invariable? It is not invariable because simply the last column was the copy of the second column. So we already know, we immediately know the third column is linearly dependent on the previous column, right? And so P will not be invariable, right? So we cannot satisfy this condition. P is invariable. So as a result, we cannot obtain this kind of similarity transformation. Okay. So in that case, the matrix A is said to be not diagonalizable. So we cannot diagonalize the matrix A into D because we cannot find invariable P. Okay, and then when can we obtain? So here the conclusion is if we can obtain 3 linearly independent eigenvectors, and then it means we can obtain the invariable matrix P. And when can we obtain 3 linearly independent eigenvectors? Or in general, if our matrix is n by n, when can we obtain n linearly independent eigenvectors? Okay, so that is our main question that we have to study today. And then we discussed about this table in order to check whether the matrix A has n linearly independent eigenvectors. So in this particular case, n is 4, right? N is 4, and suppose this was your algebraic multiplicity, okay? And geometric multiplicity, which is the dimension or the number of free variables of that particular matrix A minus lambda I, the null space of A minus lambda I, when lambda was 1 and 3 and 5 respectively. And then this geometric multiplicity should be at least 1. But also, without the proof, I mentioned that it has the maximum dimension of this null space of A minus lambda I is this value, the algebraic multiplicity. So it is 1 or 2. Okay. Okay. Then we obtain one-dimensional vector and then another dimensional vector, which are our second eigenvector. And here, if we obtain only one vector as an eigenvector, which I'm talking about the basis. Okay, so the null space, the dimension of the null space, or the null space is one-dimensional, which is just simply a line instead of a plane spanned by two linearly independent vectors. So in that case, we found only 3 eigenvectors. So in that case, it's not diagonalizable. Okay, so as a kind of necessary, the necessary condition in order to obtain invertible P or n linearly independent eigenvectors, we should at least maximize our geometric multiplicity for every eigenvalue. So basically, these two values should be the same. Okay, so that is a necessary condition. The necessary condition. It's not enough or it's not sufficient yet. Okay, so and now let's think about this case. We achieve the maximum possible value of this geometric multiplicity for each eigenvalues. Okay, and then can we guarantee that those four eigenvectors are these linearly independent? Okay, so so let's think about this and this, the maximal possible geometric multiplicity. Let's assume that we achieved that maximum number. Okay, and then we have one vector and then the other vector, and we have two vectors here, and so we have to check if altogether, when collecting all these four vectors together, are these linearly independent or not? So this is the question that we want to answer, and let's check this guy first, where we have more than one dimension as the null space the dimension of the null space. So are these two linearly independent? Are these two vectors that we obtained linearly independent? Can anyone explain why they are linearly independent? Basis. So these vectors were obtained from parametric vector form, right? And I briefly explained it last time as well. And those vectors were just a factored matrix associated with each of our free variables. And then we know those vectors attached to the free variable, those vectors are linearly independent, right? So that way we obtain like this kind of two-dimensional subspace for our null space of this A minus lambda I, right? So at least when we obtain this two, they are linearly independent within those sets, right? Within those sets. And the next question is, are these two vectors? Can we guarantee that those two vectors are also linearly dependent of this previous one or this one? Or what about these two? Okay, so here the main difference is within one matrix. So if we fix lambda, and then we will obtain a particular a minus lambda I, right? And then if that had a two free variable, and then we can guarantee that we can obtain two linearly independent eigenvector there from that case. But we now think about two different matrices. For example, a minus 3i and a minus 5i. So we have to think about these two homogeneous linear system for these two different matrices. And then the question is, the solution for this homogeneous linear system and this homogeneous linear system, are those vectors linearly independent, right? Okay, so if we can guarantee that these two sets of solutions from these two different matrices, if we can guarantee that they are linearly independent, and then that's when we can guarantee that altogether, when collecting all those four vectors, and then we can now guarantee that all the four eigenvectors are linearly independent, right? So inside of the same, or inside of each eigenvalues, okay, the number of free variable will give you the same number of linearly independent eigenvectors. And now between different eigenvalues, their homogeneous linear system solution, are they guaranteed to be linearly independent? So that is the question, right? And the answer for this question is yes. Okay, and we will prove it shortly. And so, so if the eigenvalues are different, so for the same matrix A, so we will solve the characteristic polynomial, and then suppose we obtained the eigenvalue as 1, 3, 5, and then if we pick up two different eigenvalues, and then its eigenvectors will be always linearly independent. Okay, so that is our conclusion that we will show the proof of very soon. Okay, so so with this kind of guarantee, achieving the maximum possible number of geometric multiplicity, which means, so again, like these, if those two numbers are all the same for each eigenvalues, okay, in that case we can now guarantee that we obtain n linearly independent eigenvectors. Okay, so I mentioned it as necessary condition, which is not fully guaranteed n linearly independent eigenvector, but with the additional fact that between different eigenvalues, their eigenvectors are linearly independent. Combined with this property, we can now say the maximum number of geometric multiplicity will give you n linearly independent eigenvectors, and thus, if we can find that and that condition, if we can check that condition, and then we can say that matrix A is diagonalizable, and also the eigen decomposition of the matrix A exists. Okay, exists. So this eigen decomposition is a new form of matrix factorization. Okay, so diagonalization is actually a kind of transformation of the original matrix by multiplying some matrix on the left and right in order to change your matrix A into diagonal matrix, right? So in that case, we can view it as some transformation of the original matrix A, right? But if we look at this first formula or first equation, and that has the form of matrix factorization, right? Just like what kind of matrix factorization did we learn so far? LU factorization, and yeah, QR factorization, right? So there are all kinds of matrix factorization by just combining some alphabets like ULV factorization, URV factorization, and what else? SVD factorization and things like that. Okay, so this linear algebra is mainly about so large part of contents in the linear algebra. Yeah, so up to this point we are kind of equipped. We just learned kind of solid background about the linear algebra, and using all these techniques or background knowledge, we can now play really interesting tricks by using those linear algebraic techniques in order to do various things. And although I didn't give you like many motivating example in this class due to the short time, but I can guarantee I can guarantee that all these kind of trick is the main tool for machine learning and artificial intelligence and any other statistical techniques. Okay. So all in all, we now have like a two pillar. If you're interested in the in these kind of field, the one pillar or one really background knowledge is coming from the linear algebra, and then the other comes from what? The other part comes from the probability and the statistics, and mainly about the probability, like conditional probability and joint probability, conditional independence, and Bayes rule, and things like that. And those parts will be the next semester's math class that you will take. But this kind of linear algebra and the probability and statistics, they are quite different flavor. So the style of the literature is quite different. But anyways, so I wanted to emphasize that this class is so important. During the remaining college life of yours. Okay. But anyways, So back to this. So we can view that as matrix factorization because we represented original matrix A as a product of some other matrices, right? So it's represented as a product of multiple matrices. But now, similar to LU or QR, we have our own definition, or we have our own requirement for D and P, right? So in terms of the size, when talking about the eigen decomposition, we are only considering the square matrix. So for the rectangular matrix, we cannot even talk about eigen decomposition or eigenvalue and eigenvectors, right? And so we only consider the square matrix. And P and D has the same size of the square matrix, and our requirement for this factorization is P is simply just an invertible matrix and D is diagonal matrix. Okay, and from this chapter, we learned that this matrix P and D can be obtained from eigenvalue and eigenvector pair, right? Okay, that is the main story at this up to this point, and then now let me describe where can we utilize, or where will this eigen decomposition be useful? Where can we find its use of this eigen decomposition? Okay, so if you remember the very first lecture about, see, yeah, so see, so if you remember this lecture, and or yeah, it might be easier, although I may have erased it, but in this very first slide, I introduced the utility or the usefulness of eigenvector and eigenvalues as just a way of accelerating or simplifying our computation of matrix vector multiplication. Matrix vector multiplication. Okay, so here the idea was. If we have an eigenvector and if we want to compute a times v, and yeah, we considered how many additions and the multiplications we have to perform in order to compute a times v, right? So it's all the inner product, right? By scanning each row of an a, right? And so so that is the typical kind of matrix vector multiplication. But if this v was eigenvector, and then we can just ignore this complicated process or tedious process of matrix vector multiplication, and we can just simply scale the original vector v by the amount of eigenvalues, right? So so using that, eigen decomposition or eigenvalue and eigenvector can accelerate this kind of process of matrix vector multiplication. And in that case, it may be just limited to just an eigenvector. So when can we utilize such kind of acceleration? It's only when your vector v is eigenvector, right? What if our vector maybe just an arbitrary vector x? What if our vector x is not a eigenvector? And then we cannot exploit or utilize this acceleration process from the eigenvector and value relationship, right? But we can still do some trick so that, let's see. Yeah, so if you remember this slide, and what I described here is, so suppose you have some vector x, and then suppose you found the linear combination representation of your vector x in terms of this eigenvectors. So even though you have some vector which is not eigenvector, so your vector is not eigenvector, but still you can represent this vector x as a linear combination of eigenvectors. Okay, so that is the point. So suppose these are eigenvectors, and then these are eigenvalues. Okay, sorry, these are not eigenvalues. So these are just linear combination coefficients in order to represent the vector x by using the eigenvectors. Okay, so this is the linear combination representation, right, in terms of an eigenvector. And then when multiplying the matrix A here, on the left, of course, on the left, and then we can now avoid this tedious process of matrix vector multiplication by just simply multiplying this this eigenvalues in the corresponding eigenvector side, right? Okay, so this is a important part, and this guy, this kind of thing, this process can be achieved by using eigen decomposition. So I will show you this kind of process. And yeah, so up to this point, we didn't know the reason. I mean, we didn't understand why we should understand this eigen decomposition and when it will be useful, right? And then now we will understand when it can be useful, okay, in the context of accelerating matrix vector multiplication. Okay, so let's see. Let me use some example just to be concrete. Okay, I'll use this example. So suppose your matrix A is this, and yeah, it gave you, this example gave you eigenvalue and vectors. So here, so the typical process will be to form the characteristic polynomial like this, right? And then form the second order polynomial or characteristic polynomial and the equation, and then obtain the lambda, and the lambda will be 5 and 3, right? And our P is composed, the columns of P is composed of eigenvectors, right? So we have these two eigenvectors, okay? Okay, 1, 1. Okay, then let's see. And then let me just write its eigenvalue and vector equation separately for each eigenvector and value pair. So A times 1 minus 1 and 1 minus 1. So this is the first eigenvector. So let's call this guy as V1. And what will be the eigenvalue? So 5, right? Because this guy is corresponding to this guy. Okay, then A times the second eigenvector is 3 times 1 and minus 2, right? So this will be, yeah, satisfied. Okay, and then now let's think about some arbitrary vector x as 2 and minus 3. 2 and minus 3. So this is your vector, or this is like some kind of characters that you play in the video game. Okay, this is the vector representing your character, and then you want to rotate your character like this, right? And then we have to multiply cosine sine and sine cosine minus, right, with your character vector, right? So this is determined by your controller at this moment. So that way, this is one arbitrary vector. And now what we do is to represent this guy as a linear combination of eigenvectors. So 1 minus 1 and 1 and minus 2, and some value, for example, C1 and C2 and plus. Okay, so what will be C1 and C2? By just running your brain, you can obtain quickly the solution as 1 and 1, right? 1 and 1. And let me ask the question: is this unique solution for C1 and C2? So at least we found one solution, so we can guarantee that solution exists. And from the perspective of a linear system, is this a unique solution? Why? How can we guarantee that? Because those columns are linearly independent, right? And they are actually, yeah, so let's form matrix equation form. So 1 minus 1 and 1 minus 2 and C1 and C2. Okay, so we have to basically solve this linear system. And these two are, yeah, at least in this example, we can see that they are linearly independent, right? But now we consider the case where matrix A is diagonalizable. So we consider, we assume that the matrix A is diagonalizable, which means you have n linearly independent eigenvectors. So in this case, it's a 2 by 2 matrix, and so we have two linearly independent eigenvectors, right? So this is one case that the matrix A is diagonalizable, and in that case, this matrix was our P, right? This is P, and basically the first step, in order to obtain the C1 and C2, what we have to solve is, this linear system, and also from the fact that this P is a square matrix. I mean, in the case of, in general linear system, P can be like a short and fat, or really thin and tall, right? But at least in this case, P is a square matrix, and also it's an invertible matrix, right? So this guy, our solution, or the linear combination coefficient, can be represented as P inverse X. And what is that in this case? So it should be and 1 and 1, right? 1 and 1. Okay, so far so good. And now let's think about A times X. A times X. And similar to this example, what is the solution? So we have this C1 and C2 as this original linear combination coefficient, and we just leave these two basis vectors, and what will be these two values? Those two will be what? What are these two values? 5 and 3, right? 5 and 3, because we multiply A into this guy, so we are multiplying A here, and A is distributed to each term of these two, and so A times the first vector is changed this as this accelerated form of 5 times 1 and minus 1. Okay, and for the second one, we have this. Okay, so this is our solution, and let me just represent it in a more compact form. So we are just playing some doable trick. So we created this matrix P again here. Okay, so this forms, this is composed of these two basis vectors that we have, and we consider these column vector, and these are the linear combination coefficient, right? These are the linear combination coefficient, and the first one is C1 times 5 and C2 times 5, C2 times 3, right? And I will factor this out further. This guy as this. So this is a simple but a new trick that we are going to use. Okay, so can you verify this is the same as this guy, right? It is the same, right? Okay, so if we have this column vector, this column vector, and if we multiply this diagonal matrix, and then each diagonal entry is applied or multiplied into the corresponding dimension value. Okay, so we are getting one step closer to, where is it? To the eigen decomposition form. So we have P here, and so instead of previous form, I need this guy. Okay, so these are still the same, and in that case, this part becomes D, right? D, and now we have C1 and C2, right? And what is the C1 and C2? These were the linear combination coefficients. When representing your vector x by using these eigenvectors as a new basis, right? So again, C1 and C2 are linear combination coefficients when representing some arbitrary vector x by using the eigenvectors as basis vectors. Okay, and then the C1 and C2. How did we obtain the C1 and C2, which are the linear combination coefficient here? This guy was this, right? P inverse D. P inverse times X. So that represents the linear combination coefficient. So we can replace this part as P inverse X. Okay? Okay, then let me ask another question. So suppose we are multiplying a squared, okay, a squared, like 2 times of a multiplication of an a. So in that case, what we do by utilizing this acceleration trick, thanks to this eigenvector and value pairs. Okay, so still the first step is to obtain this C1 and C2, which are the linear combination coefficients for eigenvector set as a new basis, right? And that's the starting point where we can utilize this like an accelerated matrix vector multiplication by just simply multiplying the constant, right? Okay, so once you obtain the C1 and C2, and since we are multiplying a two times, this the first basis is multiplied by 5 when multiplying a once, one time of a multiplication, okay? And if we do another multiplication, okay? So we have a first eigenvector, and then we do not change the direction, but when multiplying a, we change the length of this vector by 5 times. And what if we multiply a once again on this vector? This direction, the direction of this vector is still the eigenvector direction, right? And so this direction vector is not changing, and then the length is again multiplied by 5 times, right? So this V1 part, or eigenvector, the first eigenvector, will not change its direction, okay? But it is multiplied by the same number of multiplication of an a, okay, by using this eigenvalues, okay. And then now what? And then now what? We have to represent these newly computed vector lengths. So we have to use this new length of vector as the linear combination coefficient, just like this. And then we have to just linearly combine those eigenvectors back together in order to obtain one single vector, which is a squared x. Okay. So in general, in this case, for example, a to the power of 100 times x. And first of all, we obtain C1 and C2, right? So these are A inverse x. P inverse x, right? And then we scale each of the elements, right, by utilizing the diagonal matrix. And that diagonal matrix was lambda 1 to the power of 100, lambda 2 to the power of 100, right? So that is the same as multiplying 5 2 times, 3 times, and so on, and 100 times. So that way we stretch or expand the length by 5 times, and we do this like 100 times because we are multiplying 100 times. Okay, so here and then now these are the linear combination coefficient that we obtained, and we need the original basis, which are our eigenvectors, right? So this part will be P, and again this part will be P inverse x. Okay, and so simply a to the power of 100 times x is these two P, and P inverse part is not changing, and this part is your diagonal matrix D, but this diagonal matrix D is multiplied by like 100 times. And the multiplication of this diagonal matrix is just simply multiplying each element by 100 times, right? So that is the main point where that accelerates this matrix vector multiplication. Okay. Okay, now let's do a little bit more mathematical proof, which doesn't have a spirit. So I try to give an explanation as intuitively as possible, but there is a kind of a really simple trick. I mean, simple proof. So a to the power of 100 times x, and a has the eigen decomposition, which means p times d times p inverse, right? Which came from AP equals PD, right? When p is invertible, and p times d times p inverse, and p times d times p inverse, and inverse, and x. So we multiply these 100 times. Okay, and these two parts, right? The starting part and then the ending part, which has a p and p inverse, and they will cancel out. They will just cancel out. And so we have these p and p inverse, and this part is simply d to the power of 100. Okay. And for example, if d was 5 and 3, and is is to the power of 100 is 5 to the power of 100, 3 times, 3 to the power of 100. Okay. Okay, so so why is it actually reducing? Why is it accelerating this matrix vector multiplication? Okay, why is it accelerating really? So although I briefly explained that. Okay, the separate vector, each vector is just multiplied by a scalar. So that is the point. So that is the point where we can accelerate this process. But we can also view this kind of acceleration process from looking at this matrix form. So in general, a times x will be like in the case of an a, 7, 2, minus 4, 1. And suppose, your vector was 2 and minus 3. And you will do these multiplication and addition, basically an inner product. So it's like, so you have these two coefficients. So these two are coordinates, like an x coordinate and y coordinate. And if you remember that, this guy is like 2 times 1 comma 0 and minus 3 times 0 comma 1, right? So that way we can think of it as a linear combination representation by using the basis, I mean the simplest possible.
But minus, if we write minus 3 times 0 minus 1.
Oh, sorry, it should be 0, 1. Okay, so that is the simplest form of a basis, to form our two-dimensional space, right? Okay, and then the resulting vector is, let's do some calculation. 15, 8, right? And what is the second value? Minus 11, right? Okay, so how do we compute these values, each of these values? So this value is mixing up. So again, this guy is 8 times 1, 0, and 11 times the same basis vector. Okay, so these two linear combination coefficients was mixed and combined together in order to form this 8, which is a new linear combination coefficient. And also this minus 11 was also combined by using both values, right? Both values. But if your matrix, this part is diagonal matrix, which means, so once you obtained this C1 and C2, which is computed as this P inverse times X, and this kind of process is a kind of B coordinate that we learned, or we are changing the basis, the set of basis vectors into a new basis, and then we are computing the new coordinate, and that new coordinate is C1 and C2, right? So once you change your coordinate system like that way, okay, so again in this case, so this is a geometric view. So this is the original coordinate x comma y, and you have this point, and this point is represented as 1 comma 0 and 0 comma 1 and like this, right? So this was your original coordinate system. Now you change this guy by using a new basis, 1 and minus 1 and 1 and minus 2, right? One and minus 1 is this, and 1 and minus 2 was this, right? And your vector is now represented, so it's a little bit hard to draw. How can I draw that? Okay, so I'm gonna negate this guy, right? And we have this, and something like this, right? So this multiplier will be the new coordinate, right? Or new linear combination coefficient. So now, so what you did is to represent the same point by using a new coordinate system, right? Which are linearly independent, of course, right? But they are not orthogonal in this case. Okay, once you changed your coordinate system in that manner, in that case, now the matrix multiplication, A times X, and this guy is now C1 and C2, which is P inverse X, and this guy is the coordinate for this point by using a new basis vector, right? So that was C1 and C2, and in that new space, that new representation, instead of multiplying A, you are multiplying matrix D, right? D, which was the diagonal entry, 5 times 3. So this guy was, if this guy was 1, 1, and the resulting matrix, you know, is 5, 3, right? And so in this case, you have these two coordinates, of course, right? Two coordinates, but in order to compute each of these coordinates, you don't need to mix them up. You don't need to mix those two coordinates, right? You only need to look at the first coordinate to represent to compute the first coordinate, and then the second coordinate to the second coordinate. So that way, it's a kind of splitting the matrix times vector multiplication, which is in general like a mixing up process of the two coordinates, right? In order to generate the first coordinate and the second coordinate, we have to mix all the coordinates together. But in this case, once you move to the new space, and then the matrix multiplication is now just simply the separate scaling of each coordinate, right? So you don't need to mix the different coordinates coefficient together. So that's the point that accelerates this computation process. Okay, and then what is the process of P? What is the process of P? So it's like, so you originally have that old space where the basis is a 1, 0 and 0, 1. And then you sent your vector into the new coordinate system where the two basis vectors are the eigenvectors. Okay. From there, you just simply diagonally scale your matrices, which means you are splitting, right? Splitting these. You are avoiding the mixing of those different coordinates. Okay. And then after you do like a necessary number of scalings, and then you come back to the original space. That the process of coming back is multiplication of P, which means we are calling back, we are bringing back the eigenvector basis, and then when combining them together, and then the resulting coordinate is now represented like some value as 1, 0 and another value as 0, 1, right? The new coordinate can be viewed as this. So that way, it's like you are sending the vector from the new space into the old space. Okay, so you are calling back. So this is the main beauty or the main idea of utilizing eigendecomposition in order to accelerate matrix vector multiplication. Any questions so far? Okay, then now we probably have one thing left. One thing left, and that is, yeah, that is from this slide again. So previously mentioned that if we have if the two eigenvalues are different, and then their own eigenvectors are always linearly independent. So I didn't prove it, right? So let's prove that. So that proof is theorem 2 in the chapter 5.1. Chapter 5.1. So let's read through this theorem. So you have like r different r eigenvectors, and these eigenvectors are associated with distinct eigenvalues. So it's like this. So actually it starts from these r gamma 1 through gamma r, which are eigenvalues, and here the assumption is they are distinct eigenvalues, which means lambda 1, lambda 2, all the way through lambda r, they are all different eigenvalues. Okay, different eigenvalues, and so we will obtain, so suppose this one was 1 and this one was 3, for example, and somewhere in the middle, okay, let's do it, let's set it as 5 and then 3, for example, and then we will form a minus lambda I for each of these values, and then we will do these null space, obtaining the null space and their basis vectors, and these are eigenvectors, right? And then here we want to prove that they are always linearly independent if those eigenvectors were coming from different eigenvalues. Okay, so those eigenvectors are corresponding to distinct eigenvalues, and then collecting those eigenvectors like these, and the columns of these matrices are linearly independent. So this is the thing that we want to prove here. Okay, so we start with this kind of a contradictory assumption. So we start with the assumption that, okay, so let's assume that they are linearly dependent. Okay, linearly dependent. Okay, and then all these vectors are non-zero vectors because they are non-trivial. They should be non-trivial solution from some homogeneous linear system, right? So they are non-zero vectors, of course. Okay, and if these are linearly dependent, and then from one of the previous theorem that we learned maybe a month or so ago, we just incrementally add one vector at a time. So we start with the first vector and then check if that can be represented as the linear combination of the previous vector. So if we cannot, we move on to the second vector, and then we check if the second vector is represented as a linear combination of the previous vector, which is the first vector only. And then if we cannot find the linear combination, and then so far so good. And then we move on to the third one, and then check if this vector is represented as a linear combination of the previous two, right? And we add one by one this manner, and then at some point, if we can find the linear combination representation successfully, and then that's when that concludes that our vector set is linearly dependent, right? But if we cannot find such kind of linear representation, linear combination representation, and then until the end, and then that's when they are linearly independent. So if they are linearly dependent, and then at some point we should be able to find the linear combination representation of some vector using the previous vectors. Okay, and at some point, by mentioning that, let's denote that some point as p. So p plus 1, so p was 3, for example, at like v4, is represented as a linear combination of V1, V2, and V3. Okay, let's suppose that, because they are linearly dependent. Okay, and then that representation is written as this. So C1 through CP and their linear combination of V1 through VP, then it should be the same as VP plus 1. So it's like V4 is some linear combination of V1, V2, V3. Okay, so here again V1, V2, and all the way until VP plus 1 are eigenvectors. Okay, eigenvectors corresponding to distinct eigenvalues. Okay, so that is the property of, that is the requirement of these V's, vector V's. And so in order to utilize that eigenvector and eigenvalue relationship, we multiply the matrix A on both sides. So it's like you multiply A here and A here. Okay. Okay, and then although we have some scalar values, different scalar values, but we can move A to the right, okay, to the right side of a C1 through CP. So we obtain this and obtain this. And now we have AV1, AV2, AV3, and AV4, right? And if we multiply A on each of these eigenvectors, and then they will now be changed to its own eigenvalue times the original vector, right? So it will be changed this and this and this. Okay. Okay. Then okay. So we do one more manipulation. We do another manipulation starting from the same matrix, same equation. So now we are multiplying lambda p plus 1. So this equation was obtained by multiplying A on both sides, but we now multiply lambda p plus 1 on both sides of this same equation. Okay, and then what we will obtain is C1 lambda p plus 1 times V1, right? Because we are multiplying lambda p plus 1 and lambda p plus 1. Okay, and C2 lambda p plus 1 V2 and so on, and lambda p plus 1 VP plus 1. So this guy, yeah, so we have this, right? And so we have this and we have this, and we just simply subtract these two equations, right? And we obtain these, and the right hand side will become 0 because we have this and we have the same right hand side. Okay, and we obtain this, right? And those linear combination coefficients should be like all zeros. So that is the point here. So okay, so I didn't emphasize one thing. So this P, okay, so P, so V4, the assumption is this V4 is the first entry, so first point where we can represent this vector using the previous one. So it means the previous one, V1, V2, V3 are linearly independent. So when adding V4, and that's the first time that this guy can be now represented as a linear combination of the previous one. Okay, so the previous vectors should be linearly independent, right? And so if they are linearly independent, and in order to create 0, all of them should be 0. Or otherwise, if any of them is non-zero, and then it means they are linearly dependent, even by using v1, v2, v3, right? So that violates our assumption that before is the first entry, right? That starts to make these these vector set as linearly dependent. So they should be all 0, but these parts, v1 lambda 1 minus lambda p plus 1, lambda p minus lambda p plus 1, they are non-zero value because eigenvalues are distinct. They are all different values. So these parts becomes non-zero, and so in order to create these guys as all 0, C1 through CP should be all 0, right? And so C1 through CP are all 0, and this guy becomes 0, and so we cannot represent, okay? We now end up with violating our first assumption that we have this kind of linear combination representation, okay? Because it should be all 0. Okay, so that way we now proved this theorem too. Okay, so the time's up, and it's the end of entire chapter 6, chapter 5 about eigenvector and eigenvalue. Okay, and then next time we will move on to chapter 7. Okay, thank you very much, and that's it.
그 교재에 M이라고 나오면은 매스랩 같은 거 써서 푸는 건가요? 아니면
교재 M이라고 나오고, 네, 그 매트랩 갖고 푸는 거예요. 네.
이번에 과제 모든 문제가 다 M이더라고요.
네?
이번에 과제 몇 문제 안 나왔잖아요. 6월 4일까지인가 해가지고.
아, 그래요? 몇 개밖에 없어요? M밖에 없어요?
다 M이고 그것도 전체가 6문제.
그러면은 내가 좀 잘못했는데 그거 문제. 예. 그거 문제를 내가 좀 더 내야 되는데.
난이도가 좀 특출하죠. 헬이니까 잘.
아니요. 그거는 연습을 좀 해야 되기 때문에 그거 내가 숙제를 좀 다시 리바이즈를 하고.
기한 연장도 해주시는 거죠, 그건가요?
기한 연장? 그거 언제까지였죠?
6월
일요일까지? 그럼 뭐 이틀 연장?
네.
이틀 연장? 네, 그러면.